right, so let's get started. So we're now getting closer and closer to the end of the course. Hopefully everything went well with the project submissions. So what remains now is the last week, some new material and a little bit of review next week. And then I guess it's time to seriously start to study for the exam. But we'll cover review and exams and what is allowed on the exam and all the rules and so forth next week. So we'll continue to work on where we are in the course right now, which is on medium access control and also on local area networks. So last time we talked about LANs, so local area networks. So typically physically small networks that share a broadcast medium. LAN protocols are based in the link layer. So in the OSI stack, the lowest one is the physical layer, and above that is data link. So the LAN protocols is in here. OSI is more theoretical model. A practical model could be some other stack, for instance, IEEE 802 stack. And then we have the physical layer, we have the MAC layers, and then on top of all the MAC layers in IEEE 802 is this sort of common layer, which is called LLC, logical link control. So for all the layers which are above an 802 stack, they have the same protocol here. So it's almost like IP in the internet stack. It's something that collects everything and hides the complexities below for the layers above. So the MAC layers, we have a bunch of those. Today we will talk a little bit about Wi-Fi. We talked last time about Ethernet. So Ethernet 802.3 is a very, very common LAN protocol. And it's actually been used for fairly large networks also. There is something else called Ethernet also, an earlier version, which is called either DIX Ethernet or Ethernet 2. This is heavily used still, right? So I would say that it's not like 802.3, which is a later invention than DIX Ethernet, has taken over. They actually coexist. So they're slightly different. But not a whole lot, so they can coexist. So these MAC layers here, they provide an unreliable datagram service, which means essentially that they can send packets but don't guarantee anything. So the LLC can then enhance these services for the layers above. Typically this is not done, however, but it could. So typically what it does is basically just provides this connectionless unacknowledged service, which is essentially the same service which the MAC layers provide. LLC can provide multiplexing of several concurrent layers above it, several protocols running at the same time. It could be IP and it could be many different other protocols. Then we talked a little bit about Ethernet and the medium access method used for that. So it's CSMA CD, which is carrier sensing, multiple access with collision detection. So it's one persistent CSMA with truncated binary exponential backoff. So that's essentially what Ethernet is all about. Collision are detected, and if they are detected, the frame we are transmitting, we stop doing that and then wait for a random backoff time, which is R times T slot. T slot is a parameter which depends on physical things. R here is a random number, and it's an integer between 0 and 2 to the power of k minus 1. And where k, this parameter k, depends on at what retransmission attempt we are. So at retransmission attempt n, we take the minimum of n and 10, and that becomes k. So that means that for successive collisions, then we increase this maximum backoff time, which means that we spread retransmission attempts more in time, reduces the load on the channel, and then it's easier to get through. Okay, so typically we want to pick in general backoff times as small as possible, but large enough so we don't have a lot of delays in the frame delivery, but we also want to keep them small in order to not have a lot of delays in the frame delivery. So delay, it's a little bit of a trade-off here. So this one, this method here makes sure that we pick a reasonable back-off time to compromise between these two things that we would like to achieve. So, purpose of binary exponential back-off is to reduce the probability of repeated collisions, but with as small delays as possible. Then we went over to look at how we can interconnect several LANs with each other, and we can use then bridges to do this. There is a concept called transparent bridges, also known as switches. And these are used to connect LANs in a way so that stations which are attached to the LAN does not notice that they are several LANs actually. So it forms a logically single large LAN from a number of physical smaller LANs. And bridges, what they do is they move frames between these LANs if needed. So then they need to figure out where stations are attached to which LAN in order to move it to the right LAN. So it has to do forwarding. Pick up frames on the LAN which is attached to and figure out whether you should output that on another LAN or not. So these forwarding tables are learned by observing data which is running on the LANs. So this is something which is, the bridges learn what to do by observing the data traffic which is ongoing. So bridges do not need to be configured by the stations, and therefore the stations don't even know that they are there. So that's the word intransparent here. Okay, so we went through an example how to build up this forwarding table with a method called adaptive learning or backwards learning. And then this works very well as long as we don't have loops in the network. So when we have loops in the network, what do I mean by that? So for this example here, we have 4 LANs, one here, one here, one here, and one here. Okay, so what we would like to do is to connect these together to form a bigger LAN. So we put in bridges here, B1, B2, B3, B4, and B5. And the idea here is that the station which is attached to, say, LAN 4 should be able to communicate with the station which is attached to LAN 2 in a way without these stations knowing that they are actually on different LANs. So the bridges here need to figure out everything by themselves. Okay. So this adaptive learning works well, except when we have loops in the network here. And loops means that a frame can go from one LAN to another LAN over one bridge and then go back over one or several other bridges. Okay, and this kills the backwards learning algorithm. And we can have frames going around in these loops indefinitely and never reach the destination. So that's pretty bad. The whole system will collapse. Okay, so what we want to do now is to remove loops. And what we want to do that in the following way. So this bridge number 4, have 2 ports, one which is pointing up to LAN 2 and one which is pointing down to LAN 3. So these links between the bridges and the LANs here is governed by a port on the bridge. So what we want to do is we want from this topology to figure out which of these links, the dashed lines here, that should be disabled in order to get a topology which does not have loops anymore. Okay, so we want to remove loops by logically disable links, that it's bridge ports, such that the resulting topology is a spanning tree. Okay, so what is a spanning tree? Well, the first thing, the word spanning means that all the nodes are connected. So all the LANs are connected together with bridges. Okay. So that was what we wanted, right? And we want to have this in a tree topology, which means that there are no loops left in this. Okay, so this will be a little bit clearer when we go through the example here. Okay, any questions so far? Yes?
How do the bridges figure out that there's loops?
We will see. So this we will go through now the principle, first of all, what we would like to achieve, and then describe a protocol that achieves this. Okay. So in general, what we want to do is that we want to go through 4 steps, or 5 steps, sorry. And if we do this, we have created a logical topology which is loop-free. Okay. So we will go through an example shortly. So I will just outline the steps now. The first thing we want to do is we want to choose a root bridge. And this is the root of the tree. The tree has a root and then a number of branches down to the leaves in the tree. Okay, so we want to select the root bridge. And we do that by assigning the root bridge as the one which has the lowest ID. Okay, so in this case, all the bridges have unique IDs. You can think of them as MAC addresses as we like, but actually they're not. They have some type of ID. Okay, so then good. So we need to figure out which bridge has the lowest ID, and that we will assign to be the root bridge. And then for each bridge, except for the root bridge, we determine a root port. And the root port is the port with the least cost path to the root bridge. Okay, so we will see that later on, but this one will turn out to be the root bridge because it has the lowest ID. And then this bridge here has 2 ports, one which is pointing in this direction, one is pointing in that direction. And the root port for that bridge will be the one which is closest to the root, which is this port. Okay. So we figure out the root port for all the bridges. And once this is done, then for each LAN, we select a bridge and a port on that bridge, and we call that the designated bridge and designated port for that LAN. Okay, and what is that? The designated bridge is the bridge which has the least cost path from the LAN to the root bridge. Okay, so what does that mean? Well, it means for LAN, so this will be the root bridge, as we will see later on. And then for LAN 3, the designated bridge will probably be B4 here, because there is a low cost path from here to here. And we'll define what we mean by cost of a path shortly also. Okay. So this, I understand that this is a little bit abstract here. And then this designated port will be enabled. It's that port that connects that particular LAN with the designated bridge on its way to the root. And then for all the root ports and all the designated ports are enabled. They are put in the forwarding states. And these are the ports which are allowed to pick up frames and forward frames. And all other ports are put in a blocking state, and they are not used at all in this topology. So here, 4 and 5 essentially disables those links that are needed in order to form a spanning tree. Okay. So this is a little bit hard to understand right now, but let's go through an example, and I think things will clear up. Okay. So here's our example topology. So we have a number of LANs, we have a number of bridges, and they have ports also. So we have bridge IDs here, 3, 4, and 5. These are bridge IDs. And for a bridge B3 here, we have 3 ports, 1, 2, 3. So these are the numbers of the ports. So we have port IDs and bridge IDs. Okay? Right. So step number 1, select the root bridge which has the lowest ID. So which one would that be? Well, it will be this one, right? So then this is the root bridge. Step number 2, select the root port for every bridge except the root bridge. And here the path cost is the number of LANs in the path. Okay, so let's see how we can do that. For B2, we have 2 ports, 1 or 2, and we want to connect to B1. And if we go over 1 here, we pass over 1 LAN. So the cost of this path is 1, because we go through 1 LAN. The cost of this port is actually also 1. So for B2, both port 1 and port 2 has a path of cost 1 to the root bridge. Okay, so both of them are equally good in this case. but we select 1 because it has the lowest ID. Okay, so when there is a tie, we pick the one with the lowest ID. Okay, so let's go to B3 here. Then we have 3 ports, 1 here, 1 here, and 1 here. So let's count the cost for the path from 1 here while it goes over 1 LAN. So the cost here, the least cost path from 1 is 1. Let's look at 2 here. So what do we need to do then? We need to go over this LAN, so that's cost number 1, and then we need to go over that LAN, so that's cost number 2. So here, the path to the root has cost 2. Okay, so it's not competitive with this path. So that cannot be the root port. And let's go to 3 here. Okay, so it goes 1, 2, 3. So it has a cost of 3. So that will not be the root port. Okay. Which one would be the root port for B4? 1 or 2? 1, yeah. Here, 1 or 2? Okay, let's see. 1, 2, cost 2. Here, 1, 2, same cost. So which one will we pick?
1.
Okay, because it has the lowest ID, right? Okay, so now we know how to assign root ports. Good. Step number 3, select the designated port for each LAN. Okay, so now we go from, instead of having focus on the bridges and their ports, we go and look at the perspective from the LANs. Okay, so we need to select a designated bridge and the designated port for each LAN. So let's start with LAN number 1 here, and that's pretty easy because it's directly attached to the root. So then this port will be the designated port for that one, right? It's the closest path to the root. So for LAN number 1, bridge number 1 and port number 1 is the designated port and bridge. Okay? So let's go now to the LAN number 2. So which one will be the designated bridge here and designated port? We want to reach the root from this LAN in the closest. Yeah, so it's going to be bridge 1 and it's going to be port 2. So D here, it's in blue because it's a property of the LAN, the blue LAN, right? And this is in whatever color this is, that's LAN number 1. Okay, so these were easy. So LAN number 3, which one will be the designated port for LAN 3? B3, and why? Lowest ID, exactly. So the path from here, we can go here and here. So we need to pass 2 LANs, or we need to go here and here, we pass 2 LANs. So either these 2 could be used, but B3 has the lowest ID, so we'll pick that one. So it's the closest bridge and port to the root bridge for LAN 3, and there is a tie, which is resolved by the bridge ID. Okay, so this is the designate. Now we only have 4 here left. So let's see. What's going to be the designated one for this one, for LAN 4? Designated port and bridge. It's actually going to be B3. Okay, and the reason for this is that here we have a path that costs 1, 2. Here we have a path that costs 1. Okay, so let's see now. Did I do this right? 1, 2 is the cost here. 1 is the cost here. So actually, there was not a tie between B3 and B5 in this case. All right. So maybe we shouldn't write the tie as B result for this. Okay. So now we're in step. Now we're actually more or less done with everything. We have for each, we have a root. We have a root port for each bridge, and we have a designated port and bridge for each LAN. So I'll take that once more. We have a root bridge for each bridge, except for the root one, we have a root port. Okay, so this is a property of the bridge. And then for each LAN, we have a property for that, which is the designated port, which is attached to the designated bridge. So what we need to do now is basically go to steps 4 and 5, which is to disable everything which is not a root port or a designated port. Okay, so all root ports and designated ports are enabled. They are put in forwarding state, which means that they can accept frames and transmit frames. And all other ports are put in a blocked state, and the resulting topology is a tree. Okay, so we see here that we have removed this port, disabled this port, we disabled this port. And now there are no more loops. That is, I cannot go from one LAN to another LAN and then back another path. Question?
Wasn't the B5 supposed to have been connected to B3 to get to the root?
B5 is connected to the root via B3.
Yeah, but root 4.2.
Sorry, once more.
At least amount of LANs. If you go from B5 to the root, you go through one LAN. If you go down to LAN 4.
Yeah. So this is not a very good topology from this perspective. Yeah, exactly. So the price to pay here is that we get a tree which has no loops, but it doesn't mean that this tree, this topology, the logical topology is a super good one, right? Actually, it could be sometimes pretty bad, but at least there are no loops. Okay. So good. So now we have a logical topology here, which we can use adaptive learning to figure out the routing tables. The forwarding tables in each of the bridges. Questions? Okay. So the spanning tree algorithm needs to go through. So the principle is we want to do these things, right? We want to go from step 1, 2, 3, 4, and 5. And this is very easily done for us, right? Because we have a helicopter view of the topology. The problem is that the bridges have no idea what the topology is. They need to learn the topology, learn what other bridges are there, and then negotiate how to enable this, how to produce this spanning tree. Okay, so then we need a protocol for that. We're going to describe that shortly here. But before going to that, we see here that B4, B2, and B5 are not actually used in this topology. You see this? Because B5 here, for instance, it's not used because it's only attached to LAN 3. So it does not move packets from LAN 3 to any other LAN. So it's disabled like this. Does this mean that B5 is useless? It's a rhetorical question. It's not useless, right? Because what could happen is that if any of the other bridges here breaks, then this one would be a backup. So it's there for redundancy cases. It's maybe even more visible here. So B1 and B2 are both connecting in the physical. There is a port for B2 which is attached to LAN 2. So B1 and B2 here are really in parallel, connecting LAN 1 and 2 together. And the reason why we sometimes have these type of configurations is either we do it by mistake, a wiring problem, or we want to have redundancy. So if this one breaks, then B2 can take over. Okay, so that is indeed in the case. If this one breaks, that will be pretty bad because it's also the root bridge. Then we need to recover, and one way to recover is then to have a protocol that eventually figure out that B2 should be the root bridge in that case. Right. So even bridges which are not attached are not useless. They are sort of in backup mode when things happen, bad things happen. Okay, now the problem is of course that for us it was pretty easy to do this spanning tree thing. Now, we need a protocol to do that so that it's a distributed algorithm that does not know the topology but figures it out anyways. So this is known as the spanning tree protocol, STP. It's actually now outdated, so there is an update of this, but the general principle is mainly the same, so this one is easier to explain also. So we're going to concentrate on this one. So a spanning tree is found by the bridges by sending control packets between the bridges. These are known as bridge PDUs or BPDUs. Okay, so each bridge transmits its current guess on which bridge is the root bridge and encoded into this BPDU. So each bridge constantly transmits this, with some interval, its current guess, okay? It knows what it is, okay? So the bridge that transmits its own ID here. And then it transmits the ID of the bridge it thinks is the root bridge at this point in time, and then also the cost it takes to reach the root bridge from itself. Okay, so a station here, or a bridge, say bridge 2, will have then BPDUs that is 2, because that's the ID of the bridge, right? And then maybe it believes that B1, let's do this, B4, and maybe it believes that there is a bridge with, it knows that there exists a bridge with ID 2 because it heard from it, and it perhaps believes that that is the root bridge right now. And then the cost from going from B4 to the root here, cost C, say, and then we put the cost here. Okay. So this is the general content of a bridge PDU. Okay. So then the cost here could be the sum of all the LAN costs on the path to the root bridge. And that could be the number of LANs, it could be something else. We will see later on that there are reasons to actually have different numbers for different LANs. So each bridge stores its best BPDU it has seen so far. Okay? And the best is in the sense that the BPDU, which is stored by bridge number 4, will always have a 4 here because it's the ID of the bridge that has stored it and transmits it. But it could be that the root and the cost to the root changes because more information is available to B4. It could be at some other time it learns that there exists a bridge with ID 1. Okay? And then this one has to change from 2 to 1, and then say that this was cost number 2 and this is cost number 1 to be like this. Okay, it has to go from this to this when it learns new information. Okay, but in every instant in time, a bridge stores a BPDU, which is its best understanding at this point in time. Okay, so how do we store, what is the best, what is meant by best, okay? First of all, we want to compare maybe the current BPDU with the new BPDU that it has received. Was there a question?
How does it measure the cost? Is it in time?
No, the cost is, as we talked earlier, is the cost going from here to the root, its current understanding of the root. So, for instance, if B5 here thinks that let's go back here. If B5 thinks that B4 is the root, the cost is 1. If B5 thinks that B2 is the root, then the cost is 2 maybe. Right, okay. So it maintains, it knows what cost it is for it to be connected to the root. So, suppose that the bridge has this, x1, r1, c1, and then receives x2, r2, c2. Okay, so how is it going to figure out whether x2 r2 c2 is better than x1 r1 c1? Okay, so the first thing we want to do is we want to compare the root IDs. Okay, because if bridge x1 receives a message from bridge x2, claiming that x2 claims to have a root ID which is better than my root ID, I should update my information, because then x2 knows something that I don't know. It knows a better root. And better means it has a lower ID. So the first thing we want to do is we want to select the BPDU which has the lowest ID, bridge ID. That is, we want to compare R1 and R2. Okay. So for instance, if we had here, in this case, bridge number 4 has 4 to 5, say, and then receives from bridge number 2 1 6, something like that. Which one of these, from bridge 4's perspective, which one of these is the best? So yeah, okay. So bridge 4 currently stores this. It knows it's 4. It has it thinks root is number 2, and it has a path 5 cost to it. Then it receives a BPDU from some other bridge, from bridge number 2, namely, that says, okay, I think bridge number 1 is the root. I have a path or cost 6 to it. So what should bridge 4 do then? Well, it should select the best one of these two. So which one is the best?
It should change its bridge root.
Exactly. So this one is better than this one. Okay? So it should discard this one. But since it's bridge 4, it should put in its ID here. Okay, so this is what is stored now. And the reason for this is that it learned that some other bridge has heard of another bridge called 1, which is better than what my current understanding is as B4, because I heard about a bridge called 2. Okay. So 2 cannot be the root because there exists a bridge with ID 1. Okay. Secondly, if there is a tie, so both of them have the same root, then we compare the cost to it, to this, and we select the BPDU with the smallest cost. So, example here, if B4 stores 4 to 5 and then receives from 2 the following BPDU 2 1. Then this one wins out because there is a tie here, but 1 is less than 5. Okay, which means that this is the winner. Okay. So when comparing BPDUs, we first compare the roots and then we compare the cost in that order. Okay. So how do we start up? On power up, none of the bridges knows anything about the topology. So what do they assume? They assume that they are the root. Okay. So bridge X believes that it's the root and stores then the BPDU X. Okay, it should be actually, it can never be 1 here. It has to be 0. The cost from going from itself to itself is 0. We go over 0 lawns to do this. Okay, that's a minor detail. Okay, so the initial BPDU for all the roots is XX0. All the bridges know thinks they are the root, and the cost to go to itself is 0. So I'm X, I think the route is x and the cost to reach x from myself is 0. Then these are broadcasted on all ports, outputs on all the LANs. And then when a BPDU, say XRC, is received on a port Y, what do we do then? Well, first of all, we add the cost to the LAN which we heard this from. So suppose that the LAN cost we heard, the LAN from which we received this BPDU has cost 1, then we can form XRC plus 1. And then we compare this updated BPDU, XRC plus 1, with the currently stored BPDU. And if better, we save the new BPDU and we set port Y as the root port and stop transmitting BPDUs on that port. Okay. So. So suppose B4 has, let's say it starts with this 440. Okay. And it's connected to two LANs, LAN 1 and LAN 2. Now suppose from LAN 2 it receives a BPDU saying 220, okay? Meaning that somewhere along the LAN there is a bridge 2 which has stored 220 because of its power up, okay? So to make this clear, we have here 440, okay? So this one is output on this LAN. It's also output on other LANs, like this. So it's picked up by B4 now. So what's B4 going to do? Well, it has stored 440. It has received 220 on this LAN. Okay. So then what it do is compare it compares the current BPDU with what it heard, where we add the cost with 1, because it went over this LAN, with 221. Okay. So which one is best here, 440 or 221? (221) is the winner. So what we do then is to update to 221. So we replace 440 with 221, and then make port, say this was port 1 and this port 2 a root port. The root port. Okay? And then it makes this the root port. What to do then is to stop transmitting the BPDU on this, right? There is no need to transmit this one because there is a better BPDU on that LAN. So this current BPDUs, that is 221, would be then output on this LAN here. And eventually what's going to happen is that only the designated bridge will transmit BPDUs on a LAN. Okay, so After some time, the bridge with the best BPDU will transmit its BPDUs on this LAN, and then that will be the designated bridge after some time. And then everything has converged. So it's very simple protocols. We transmit these BPDUs, which are stored. Whenever we hear a BPDU, we compare it to what we have. If it's better than we have, then we make that port a root port and then stop transmitting on that. And eventually, we have root ports on all the bridges. All the bridges have a BPDU which is correct, and the bridge who is still transmitting BPDUs on the LAN will be the designated bridge for that LAN. And then we just all the bridges disables those ports which are not D or R, and we're done. Questions? You essentially just had to do this a couple of times to convince yourself that this is actually a correct protocol. Now we talked a little bit about this spanning tree protocol and LAN costs. And here we said that the LAN cost is essentially the cost, each LAN has the same cost, and then we can put the cost to 1. Now there is a difference, however, and that has to do when we have LANs with different data rates on it. So we might have, for instance, a LAN which has 10 megabits per second and another LAN which has 100 megabits per second. Then it actually makes sense to say that the cost of passing through that LAN is, we can think of that as the cost in time. Okay, so passing a frame through a LAN with a higher data rate takes shorter time than with over a LAN with a lower data rate. So LANs with higher data rates have lower cost than LANs with lower data rates. So the spanning tree protocol 802.1d, to be exact, LAN costs are as follows. So if we have data rate on the LAN and then the cost, then there's a table like in megabit per second. So if we have 4 megabit per second, then the cost is assigned to be 250. If the cost is 10 megabits per second, should the cost be higher or lower than 250? Lower, exactly. So it's 100 actually, and then we keep on going like this, and then for a 10 gigabit per second LAN, then the cost is 2. Okay. I mean, the numbers here are not important, but if we think of a frame that should be moved from one point to another, it has a better route if it goes over faster links than over slower links. So if we have 2 slow links, could be a worse path than 10 fast links. Right? So if we have 10 of those, 10 times 10 LANs with 10 gigabit per second, what is the cost then? Well, it's 20, right? And that is a better path than over one LAN with 4 megabit per second, say, because that has cost 250. So for sure, if I had to pick a path here and jump over 10 LANs, I would do that rather than over this LAN. because this one is extremely slow. So it's like getting to Los Angeles, for instance. We can take the boat, or we can take multiple airplanes. I'll go for the airplanes, even though there is just a single boat. Okay, so let's take a break. Kan du stänga av den där? Trycka på röda knappen.